Hello. So in the last video we set up input handling and basic player movement. Now I'll get started on handling the player's body rotation. So now in the script I have added this function called handle body rotation into physics process. I defined the function down here. I started by getting the camera base's basis and the basis of the character body. If you don't know, a basis in Godot is a 3x3 matrix used to represent the rotation and scale of an object. This matrix's X, Y, and Z columns each represent the object's respective local axes. These axes will be orthogonal to each other, which means they form a right angle to each other. But if the object's scale isn't uniform, and uniform just means that X, Y, and Z are all equal to 1, then these basis vectors will not be normalized. So with an object with uniform scale, the object's basis will be extremely useful for working with 3D rotations. We can access the object's forward-facing direction through global transform.basis.z, and then global transform.basis.x would be the object's right-hand direction. Now that we know which way the camera is facing, we want to know the difference between the rotation of the body and the rotation of the head. To do this, I'm gonna do a little math. Don't worry, math isn't scary, math is cool and awesome. So if you've gotten this far in Godot, chances are you've heard of the dot product. If you don't know what the dot product is, I highly recommend watching Freya Holmer's videos on vector math and the dot product for game development. I'll put a link to that playlist in the description. So if you haven't heard of it, here's what you need to know. The dot product is a mathematical operation widely used in Euclidean geometry. And here's the formula. Don't worry about this because Godot has a built-in dot product function, but it's important to know what it's doing. The dot product is useful for projecting one vector onto another. But what does that mean? Kahn Academy explains it pretty well on their website here. You can imagine the A vector casting a shadow onto the B vector so that it crosses at a right angle. So now if you want, you could think about this new point on the B vector as its own vector, C. However, the dot product only tells us the magnitude of this vector, not its coordinates. Now, how do we take all this information and find the angle difference between the two vectors? Well, the dot product of these two vectors is going to be equal to cosine of theta. So if we look back at our dot product visualization, you can see that visually projecting the vector onto the other like this creates a right angle. And in geometry, the angle that we are measuring, this one right here, is represented by theta. If you remember, all the angles of any triangle will always add up to 180. So the final angle here would be equal to 90 minus theta. I think that's right, but that's not important. What's important is that the dot product of two Cartesian vectors is equal to the cosine of theta. This means with theta representing the angle in degrees, in Godot we can get the angle between the two vectors if we cancel out cosine with its inverse, arc cosine. This will give us the desired angle in radians. See, that wasn't too bad. And guess what? It all paid off because now in Godot, this angle can be easily calculated with this line of code right here. But I did a little thing. If we found the dot product of the angle between the camera's forward direction, transform basis.z, and the character body's forward direction, it would give us an unsigned angle between the two, which means we don't know which way to rotate the body. A signed angle, on the other hand, would mean that a positive number would mean rotate the body one way, and a negative number means the other way. So instead, we just find the dot product of the camera's forward direction and its perpendicular axis, which would be global transform.basis.x, which is the character body's right-hand direction. The product will be negative if the angle is obtuse. So in Godot, we find the angle between the two with var signed angle equals arc cosine body basis dot x dot cam basis dot z. Next I have the threshold, which is the maximum angle that I want the head to be able to rotate from the body. I know when I set up the animations I set them up at 20 degrees, but I know from right now that the system looked much better when I used 20 degrees for this threshold value instead of 20. If you use this method, you can play around with this value. Next, I'm going to want the player's body to automatically align with the camera if the player is moving forward or within a certain angle of the view range. To do this, first I'm going to take the movement direction and construct a basis object out of it. When making a basis object, we know that it should consist of 3 vectors, the object's local x, y, and z axes. So we can think of the movement direction as our forward direction, like basis.z. So to make the rest of the basis object, we will need to get the y and z components. Now first of all, we know that the y component for our situation will always be the global vector3.up direction. Now since we have the z and y components, we know that the x-axis is perpendicular to both the z and y axes. So this component can be found using the cross product. The cross product is an operation like the dot product, but it returns another vector that is perpendicular to both vectors, which is exactly what we need. So in this line of code, to find the move basis, the x component is the cross product of vector3.up and our cam movement. The y component is just vector3.up, and the z component is just cam movement. If you want to know more about the cross product, again, go check out Freya Holmer's videos on vector math, link to that playlist in the description. Next we're going to find the angle the same way we did before, but this time we get the dot product of moveBasis.z and camBasis.z to get an unsigned angle instead. Then I clamp it between -1 and 1 because I only want the body to align with the camera if the move direction is generally forward. Now here's where we actually rotate the body. If the signed angle is greater than 90 degrees plus the threshold value, then we calculate the amount to rotate the body and then we rotate it. The reason it says 90 plus threshold is because since we use the dot product of the camBasis.z and bodyBasis.x instead of bodyBasis.z, when the camera is perfectly aligned with the body, the signed angle value will read 90 degrees correctly. If we did the dot product between camBasis.z and bodyBasis.z instead, when the camera is aligned with the body, it would return 0. You can also see that I used the lerp angle function with delta here instead of directly setting rotation.y. to smooth out the motion. And lastly, if there is any player velocity, then we check to see if the unsigned angle we calculated is greater than some arbitrary threshold you can decide. I wanted the limit for this to be 60 degrees on either side. I also took this line of code from the movement function and instead just placed it at the end of physics process because I want this to be the last thing that happens every frame. Now let's build the game and try everything out. And look at that, the body rotates the way we described, and when we move forward, the body rotates to align with the move direction. So in the next video, we'll be setting up the animation tree, and after that, we'll start setting up the hand tracking, walk and run animations, and the punching animations. After that, I'm going to start another series parallel to this one, which will be the same kind of workflow tutorial series for an enemy zombie AI that we can use to set up a combat system for this player controller. So if you want to see how I implement combat into my player controller, you'll want to see how I set up my zombie AI. See you then.